My name is Matteo Salvarezza. I am the lead developer of the machine learning framework at Wolfram Research. And this talk will be about the PyTorch backend for the neural network framework. So, as you might know, the neural network framework is undergoing a migration for the backend used for computation. We are migrating from MXNet to PyTorch, and this talk will show what's the status of the project essentially. So before we start, a few setup steps. If you wanna follow along the presentation, you need to run this cell, which is gonna download and install a Packlet for you. Yeah, for me it's saying I already have the Packlet because I already did it, but for you, you should just return the Packlet object. If you are on Mac, you also want to run this cell that's gonna download and install a different Packlet for GPU support. These Packlets are only compatible with the 15.0 beta version that you should have installed. When the released version of 15 of Wolfram Language 15 will come out, they will not be picked up by the release version, so they should not create any problems. But just in case, you can run this cell to uninstall them. Lastly, you will run this cell to get this just defines a string that identifies your GPU device, whether you are on Mac or Linux and Windows. Obviously, if your machine doesn't have a GPU computation will not work anyway. I see there's a question. Can you increase the font size on your screen? With this presentation, okay, well, I can. Problem is, I'm not gonna be able to, because I will have to make the presentation full screen, and I'm not gonna be able to check questions. So, okay, I'll do this. Oh, wait, no, I was just wrong. There's a magnification button, sorry, okay. We should be good now. Okay, let's keep going. Hopefully, in the meantime, you all have installed the Packlets. Okay, so here's an overview of the talk. I will first make an overview of PyTorch Link and comment on its progress. Then we're gonna check how PyTorch Link, which is the link to PyTorch that we are developing, is going to be useful outside of the domain of the neural network framework. And then we're going to focus on the neural network framework and show how you can use PyTorch Link, what's supported, what's not, and make a final overview of all the backends used by the framework. Okay, so let's start from PyTorch Link. So I gave an equivalent talk to this at last year tech conference. And so in the last year, we kept working on it, and it has enjoyed a lot of progress. We have added hundreds of operators. We have an automated system to do that now. We have added GPU support for both NVIDIA and Apple GPU, higher order gradients, and completely general backward pass capability and complex number support, and other minor features. So a few notes. So despite its name, there is no Python in PyTorch Link. It is a direct link between the Wolfram language and the C++ library that's used by the PyTorch package, which is still part of the PyTorch project, but it's C++. Also, this is not user-facing functionality, so you will never find a mention to this in the documentation. And its function can change without notice across WL versions. This is an internal Packlet whose role is to back the top-level neural network framework and possibly other areas of system functionality. Okay, so you can load PyTorch Link with this command. With this command, you can check the documentation of all the exposed functions and symbols. So you can click on each one of these, and it's going to tell you what they do. I'm gonna make an overview of the Packlet, but I'm gonna skim over a lot of things because there's not enough time. So you can play with it if you want. Lastly, if you are familiar with the Python package for PyTorch, like the terminology and feel here is very similar. So if you're familiar with that, you should find your way around here pretty easily. Okay, so yes, let's start from tensors. So tensor is the data structure, the basic numeric array data structure for in PyTorch. Again, you can check the documentation of PT tensor create, which is the main functions you're gonna use to interact with them. It's also somewhere here, and you can click on that. Okay, so at the basic level, you run PT tensor create, you pass a numerical array inside of it, and it's gonna give you a tensor in PyTorch. You can read the data back from the tensor using PT tensor get. And this, by default, it's going to give you a numeric array with the same data type of the tensor. Or you can pass returned object goes to list, and then it's going to give you a packed array. Or you can run normal on this numeric array. But returned object list is more efficient because it skips one step. Okay, then you can pass the data type in the second argument. So the default data type is 32, but you can pass something else, and this is going to create, for example, a 16-bit real tensor. And you can also create a tensor on the GPU. So here we're going to use our GPU device. So yeah, I'm at the moment I am on Windows, and this for me says CUDA. If you're on Mac, this should say MPS. If you're on Linux, it will also say CUDA. And if you don't have a GPU, this will just fail. Okay, so what do you do with tensors? Well, you feed them to operators to compute whatever you want. So in PyTorch Link, and this is one of the few differences with the Python package, all operators are accessed using this syntax. So this PTOP symbol, then you put the operator name here, and then the arguments. In the Python package, some of operators are classes, some are methods of tensors, some are functions. Here, they're all functions, and they're all accessed in this way. So what you can put in here and what you can put in here is given by these $PT operators arguments. So there are 975 operators. The keys of the associations are the available operator names. And the values are what the signatures, the arguments that they take. So let's pick a couple of famous ones. I'm using this general utilities pretty form just because if you don't do it, it's gonna have these long internal names which are cumbersome to read. So you can just do this and it's gonna be nicer. So this is telling us that the relu operator takes a single argument, which is a tensor, and the linear operator takes 3 arguments. They're all tensors, input weights and biases, and the biases are optional, and you can also pass none. Now, $PT operators arguments only contains the operator names and their syntax, and their signature, but not their documentation. Like they don't tell you what the operator does. These operator names that you can put in the first argument of PTOP, they are the same, and so which also appear in this association. They are basically the same as the Python wrapper, the Python package. So you can check the documentation for the Python package for any operator, and then you can check $PT operator arguments. If you find an entry here, it means that the operator is supported in PyTorch Link, and you can use it with the syntax it gives you. Okay, so with that being said, let's run an operator. Let's run the linear operator, defining data for input weights and biases, creating tensor for them, and then I'm running PTOP. So this gives me back another PT tensor, which I can just read back with PT tensor get. Now I can build an equivalent linear layer in the top level framework that's gonna run with NXNet in this case. And yeah, it produces the same result. Now, how do you do GPU computation? Well, you just create the tensors on the GPU. So again, use GPU device, and then do the same exact thing. You call the operator in the same exact way, and this time it gives you back a tensor that lives on CUDA. So it's a device is CUDA 0. 0 means it's the ID of the GPU. I only have one GPU, so it's going to be 0. Okay. Yeah, and again, you can get the output, and you can see that the results agree with the CPU computation. So all the operators must live on the same device. If you try to feed all tensors. If you try to feed a tensor on GPU and a tensor on CPU, the library is going to complain. Then there are other operators that are outside the PTO proper, and these are mostly arithmetics and in-place arithmetics operators. So you can do stuff like summing tensor using plus, and this performs the sum in PyTorch and gives you a PyTorch tensor. And same like here, this example, I have exponentiation, and you can get the results, and they do what you expect. There is also in-place arithmetic. So I'm doing t divided by equals 4.5, and then I check again t, and the data is changed. And then there's part extraction. So you can run part on these tensors with both Torch and Wolfram Language semantics. So in Torch semantics, you have zero indexing, and span and positions are not included. So let's see an example, creating data in the tensor, and I'm running part on this tensor, and it's giving back another tensor. Again, this part is performed by PyTorch. Yeah, if you want Wolfram Language semantics, you have to pass the WL part goes to true, and these are basically with the different semantics, these are equivalent calls. So you can get these tensors, and you see that the data they have is the same, and then we can also check that the part operation done in the Wolfram kernel on the basic data is equivalent. Okay, next is gradients. For gradients, just like with the Python package, you have to set the requires grad flag to true. Then you can run a forward pass, so feed it on operators, and then you can perform the backward. So this is the tensor creation with requires grad true. Then I'm essentially running the sign. I'm taking the sum to make things easier for backpropagation. Otherwise, I would have to use an outgrad. And yeah, and then I can run the backward pass on the output. So this doesn't return anything, but what this does is that it has populated the gradient of all the input tensor which had requires grad to true. So in this case, it's just input, and the way I actually get the gradient is by running pt tensor gradient on the input. So this gives me another tensor, and this time this is the gradient. So I can grab the data from it, and I can double check. What I've done is essentially the gradient of the sine operator. So I expect this to be the cosine of the inputs. And if I run the cosine of the input in the Wolfram kernel, it's the same results. Note that if you want to play with this, you might encounter this kind of failure. This happens when you run pt tensor backwards twice without resetting gradients or doing anything else. This is not allowed in the library, so yeah, watch out for this. You can do higher order gradients, and you do it by calling the backward repeatedly and setting create graph true to the backward. And let's see an example of that. So the forward pass part is the same. I'm running tanh here. Now here I want to calculate the fourth order gradient. So I have this loop that runs for 3 iterations, which computes the backward, and then I have another call here. So I'm calling the backward 4 times, as you would expect. And basically, you see the first time I'm running the backward on the output of the computation, but then I'm doing output equals gradient. And then I'm doing the gradient again. So I'm doing the gradient of the gradient of the gradient of the gradient, which is by definition the higher order gradient. Details I'm skimming over. You have to reset the gradient. If you're familiar with PyTorch, you understand this. Otherwise, you can go look for how it works. And I'm also skimming over the fact that here we are using outgrads because after this tensor is not a scalar anymore, and so you need an outgrad. You can read the documentation for pt tensor backward and generically how backward pass is working in any neural network framework, really. Okay, so here's our final fourth order gradient. It's again a tensor, and I can grab its output and I can compare with the fourth order gradient calculated symbolically using the Wolfram kernel, and yeah, the result is good. Again, I invite you to read this documentation if you want to know more about pt tensor backward. Okay, now I have a full example of evaluation of a pre-trained LeNet model that we grabbed from the Neural Net Repository, but we evaluate in PyTorch link, and also a full training example, but I'm going to skip them because there's not enough time. they're here. You can play with them if you want. Now, I want to highlight the fact that PyTorch Link can be useful outside the domain of the neural network framework. And it's because it offers a lot of optimized operators that are easy to use. It supports GPU devices, and for stuff like signal processing, like image and audio processing, there's way it can be put to use. So this is an example where I'm defining this PyBlur function that takes an image and blurs it using a 2D convolution in PyTorch Link. So we get this PyBlur. I'm not gonna go in detail in the code, but you can see this called to ptop conv2d. This is the convolution. Then I also have a PyBlur separable, which is basically the same thing, but in a more optimized way that separates a convolution that can be expensive into two less expensive convolutions that are technically two-dimensional, but actually one-dimensional. Okay, so I have these two functions. I can compare them versus Gaussian filter, which is the equivalent system function that does the same thing, that can do the same thing. So I can define an image and a radius of 50 pixels for the blur. So this is quite a large radius. And let's see what happens. I'm calling PyBlur separable Gaussian filter, getting the results and computing the timing. Now, this is platform dependent. Here I'm on Windows. On Windows and Linux, a PyTorch Link with 64-bit precision is quite bad. And in fact, you can see here that the timing is a lot larger in both cases than Gaussian filter. On Mac, this looks better. This distance matrix is basically to check that all the results are equivalent, and you see that the differences, the average difference is very, very small. Now, let's go 32-bit precision. Well, with 32-bit precision, you can already see that, at least on this computer, the PyBlur separable is beating the system function. And results are still good. And then you can obviously go GPU if it's available. And in this case, it's even better. So in this case, or even the non-optimized beats Gaussian filter. And the results are still good. So this was just an example. There are also for audio processing a bunch of Fourier transform operators that you can check. They all start with F15 something. Okay, let's talk about PyTorch Link in the neural network framework now. So we have started to hook it up, and it's partially hooked up. It's still in development. What it's supported is net evaluation, so containers and about 50% of the layers, evaluation gradients, and GPU evaluation. What's not supported is variable length inputs, which we are currently working on. Net encoders and decoders, this is easy. I just didn't have time to do it yet. At the moment, they are ignored, like the network are evaluated as if they don't have any encoder or decoder. And then there's net train and net measurements that are still to come. Okay, so how do you use it? How do you do torch evaluation? So the way you do it is you set this runtime option, evaluation backend goes to torch. Now, the evaluation backend option will be documented. The value torch for it will not be documented yet. So let's see an example. I got extract encoders and decoders, again, because they're ignored. If not, I can grab a few MNIST images, and what I'm doing here is that I'm pre-encoding the images separately, then I'm running them the network with evaluation backend goes to torch, so we go through PyTorch Link, and then I'm decoding, and yeah, it works. You can do gradient and GPU evaluation. Here I am just removing the final softmax, otherwise the gradients would be all zero, basically. And I'm doing the same thing. I'm not decoding, and I'm grabbing the output and all the gradients. And then I'm setting evaluation backend torch, target device GPU. And there you go. You have everything. Okay, so target device GPU will route to either CUDA or Metal, depending on the platform. So the GPU device thing we defined earlier. Obviously there's a similar system to select exactly the backend we want. Now, keep in mind, all of this is still very experimental. It's not tested thoroughly. You can expect problems and stuff that fails in weird ways. Like, for example, at the moment with variable length inputs, if you try to evaluate with evaluation backend torch, this tells you data supply to port input was a 3-length vector, but I expected a vector. So that's just stupid. But yeah, it's still work in progress. And if the layer is not supported, like it's not implemented in PyTorch yet, you will get expressions like these in the output. So yeah, beware. If you want to see what layers supported, what layers are not, these are supported layers. These are the layers that we still have to hook up. Okay. Lastly, I want to take a step back and talk more generally about the backends, all the backends in neural network frameworks and how they are used and what's the scenario. I'm afraid. Okay, now I have to dial this back because you cannot see the picture. Let's. Okay. So this illustrates the available backends and devices for net evaluation only. Outside of net evaluation, there are 2 other entry points for computation. One is net train and one is net measurements, but they still only support MXNet. So for net evaluation, we have net external object, which is like a satellite of the framework, which is explicitly tied to a backend. And this net graph stands for everything else in the top level framework. So layers, containers, graphs, chains, whatever. So these are the backends that these things can use, and these are the devices that these backends can use, okay? So from 15, you will be able to select, like, from this column and this column independently using evaluation backend, again, and target device. So you can set combinations of it. So I can try to maybe find a middle ground. Okay, so yeah, what's to say about this? The default value for evaluation backend is automatic, which will basically try to select a backend depending on what you have selected for device and what operating system you're on. So I suggest, if you want to experiment with this, you set the evaluation backend to what you want so that you can control exactly like which path you are taking here. Yeah, allowed values for evaluation backend are again automatic, MXNet, Onyx runtime, and Torch will be undocumented. Evaluation backend automatic also never results to Torch for the same reason, because it's still half baked. Yeah, these I already mentioned. You can set this global variable to any of the backends to force it by default, but its value is ignored if you also pass the option. So for net evaluation codes where the option is passed, the option is taken. Otherwise, you can set this. And also keep in mind that obviously not all combinations of backend and device are valid, because not all the paths are possible here. Like, for example, if I say an evaluation backend is MXNet and target device is DirectML, well, this throws an error message because MXNet is not connected to DirectML. On the other hand, Onyx runtime is connected to DirectML. So like this, on my machine, this works because I'm on Windows. This DirectML is only a Windows thing. So if you're not on Windows, it will still not work. So like if I wanted to make this in full detail, I should have like crossed out some paths depending on the operating system. But yeah, it was already complicated, and it's pretty clear that Apple GPU, is Apple, and Apple Neural Engine. Yeah. Okay. Yeah, that's basically it. So again, when you set evaluation backend to Torch, target device metal becomes available to use the GPU. So it's this path here. Or as you've seen before, you can also set target device goes to GPU. GPU is a meta setting since the latest version, since like 14.3, sorry. that translates to one of the others depending on the context, essentially. Platform, evaluation, backend that you have set, the target device, available hardware, yeah. So that's that. And yeah, as I also mentioned, net external object is explicitly tied to a backend, so there is no evaluation backend option for it. Like this step is already set, and you can select based on what backend the net external object is using. You can select only the device. And that's it. That's it, basically. I see there were no further questions. If there are some. So PyTorch link works on Linux Mac? Yes, it does. Yeah, on Mac, if you want the Metal support, you have to download the packlet, the additional packlet that it's at the beginning of the presentation. On the other platforms, you don't have to do anything. And also on Mac, if you don't download that, it will use a PyTorch link version that's in the installation layout, which is a little bit older, doesn't have Metal, but has all the other stuff. Oh, I installed the package and I got an error message. What Wolfram Language version are you on? These only work on the 15.0 beta version that was made available for the conference. Also, like if there is no PyTorch link at all, like this means you are not on 15 anyway, because again, even if you don't install the packlet, there is a PyTorch link version in 15, in Wolfram Language 15. So if it's not finding that, there is also nothing to do with installing the packlet. It should still find some PyTorch link if you're on 15. Okay, so thank you very much, everybody. Enjoy the rest of the conference.